Well, hello and welcome to our Unit 7 in 110 Acoustics. It's only April 16, but nonetheless, I'm doing the Zoom session that we would have done next week, Tuesday, but I'm gone to Europe next week from April 20 to April 30. So I thought I would just hold this Zoom session today before I go. So that's why we're holding another Zoom session today, April 16, on Unit 7, Non-Electronic Acoustic Modifications. This is your final unit of the course, and it's here where we will really talk turkey about acoustics in hearing aids. Non-electronic acoustic modifications. Look at kind of a long bucket, just a long sentence. Nothing to do with the electronics. Nothing to do with circuits and wires and stuff that's inside. It's more to do with the shape of the hearing aid and what it does. So I'll show you examples, but let's cut to the chase and share screen and look at our notes that I have uploaded onto Unit 7. When we look at those, you will see non-electronic acoustic modifications. I'll make it a little bit bigger. All right. It's a lost art. Most of today's hearing aids are digital, which allows for amazing amounts of frequency shaping. Stop there for a second. Yes, what we do with hearing aids is shape the sound. In other words, we take the audiogram that might show hearing loss in the high frequencies and maybe good hearing in the low frequencies, and we'll make the hearing aid provide lots of treble amplification, high frequency amplification, and very little bass amplification. So like an equalizer, we can shape the frequency response of the hearing aid. In other words, we can shape the spectrum of sound that the hearing aid puts out. You can put out a broad, flat, like a white spectrum or a pink spectrum or whatever. You can shape the sound of hearing aids. In so much so, I'll stop sharing for a second. If you look at my fingers like this, we can do this, we can do this, we can do this in terms of frequencies, of lows here and highs over here. We can do this. You can do anything you want. You can even do this. Okay? The point is, hearing aids all have channels, and you can raise or lower the amplification in any of the thin little channels. Just like we talked about in masking, you have bands of noise. Well, you can raise or lower frequencies in a hearing aid to match the shape of someone's hearing loss. Okay? That's electronic. But today we're talking non-electronic acoustic modifications and what happens. But non-electronic acoustic modifications are techniques that were used a lot more yesterday than today, but we still use one of them today a lot. And when fitting, they were really handy when fitting quite inflexible analog hearing aids. Okay, now here, analog is not digital. And analog hearing aids, you could shape the frequency response a bit with them, but not as much as you can do today. Today's hearing aids are very flexible, okay? Anyway, non-electronic acoustic modifications do help to shape the frequency response, and any good HIS should have a handle on them. Besides, implementing the principles is cheap. Now, remember this one that we've covered in anatomy and also in acoustics. The resonance of the outer ear canal. It's a quarter wave resonator. It's a cylinder open at one end. So it's a quarter wave resonator. It resonates when sound waves are 4 times as long as it. So the ear canal is 2.5 centimeters long. 4 times 2.5 equals 10 centimeters. 10 centimeters equals 0.1 meter. So figuring out the frequency, 0.1 is equal to 0.1 over 1 is equal to 340 meters per second over x. Okay, you're trying to find out what the frequency is. Frequency is speed of sound over wavelength. Wavelength is speed of sound over frequency. Okay, so you're trying to find x. You know the wavelength. You know the speed of sound. So you just do the old fraction. And 340 divided by 1 is 3,400 hertz. So the resonating frequency of the ear canal should be 340 hertz, 3,400 hertz. But the ear canal, external auditory meatus, is flesh and bone and cartilage, so this resonance is spread out. So here we go. The resonance is spread out across 1,500 to 4,000 hertz. And the peak ear canal resonance is around 2,700 hertz in the average adult, slightly higher in a child because they have a smaller canal. But hearing aids plug up the canal and destroy this natural key of listening because now the ear canal is closed at both ends. So the hearing aid thus has to help restore this lost resonance and also make up for the hearing loss. And we know that 2,000 to 4,000 hertz are very important for understanding speech because that's where the soft, high-frequency consonants are. And consonants tell you what the words were. Some ear molds of hearing aids don't allow enough highs to get into the ear. So for high power behind the ear hearing aids, beware of old, narrow tubing. So we'll talk all about this stuff. Let's look at our pictures here. In our PowerPoints, here we go. We'll blow that guy up and make it big. Here you go. So here's an open ear canal at the top. And here's the ear canal. It's 2.5 centimeters long, and it's going to result in this kind of a resonance, right? It starts around 1,500 hertz, ends around 4,000 hertz, with a peak at around 2,700 hertz, and we perceive that as normal. Okay? Here's sound from a speaker, and it goes into that open ear. But look at here. Now you've got a hearing aid, the bottom one, and it's plugging up that ear canal. And the hearing aid is hanging behind the ear, and it has a tube going into the ear mold. And that's an ear mold. This is what fits inside of your ear canal. So the hearing aid might be putting out a frequency response like this, okay? But because you've cut off this resonance here, you've lost some of that high frequency stuff. You can't really expect it to be doing exactly this in the ear canal because you've blocked this off, okay? You no longer have a quarter wave resonator. So here's speech. More energy in the lows, less energy in the highs. This is the spectrum of speech in dB/SPL. You got 100 hertz here, 1,000 hertz here, 10,000 hertz here, okay? And here's your decibels. Average speech, most of the energy is in the lows, so it has a spectrum a lot like pink noise. And here's the sounds of speech, the letters that are so important to hear. Okay, the high frequencies are soft and the low frequencies are louder. So let's make sure we understand the axes here. This is an audiogram, okay, and here's 0 dB hearing level, and the decibels are increasing when you're going down, okay? Now, this little line here kind of bugs me, so I'll fix it here. This kind of bugs me here. Let's see, this guy right here. Get rid of it. Okay, now we'll make it bigger again. There. All right, so you have this audiogram, and it's plotted in dBHL with the decibels going down, and this one here, of course, is plotted in dBSPL with the decibels going up, okay? So most energy in the lows, this is speech spectrum in dBSPL, and this is the speech sounds on an audiogram, okay? Same thing. So when you start, that's the beauty of the outer ear canal resonance, is it largely amplifies a little bit. It resonates with those soft, high-frequency sounds, with the soft, high-frequency sounds. And we've said time and again, that's why the shape of the ear is why it is, okay? Because the concha bowl resonates between 5,000 and 6,000 hertz. The ear canal resonates between 1,500 and 4,000 hertz with a peak at 2,700 hertz. So here's the outer ear canal resonance shown closer up. All right, so you've got the ear canal resonance starting at around 1,500 hertz, ending around 4,000 hertz with a peak at around 2,700 hertz. The outer ear adds decibels to the high-pitched consonants of speech. And here's a very common hearing loss, the X's and O's. Very common, presbycusis, high frequency hearing loss in the elderly. Good hearing in the lows, poorer hearing in the highs. They can't hear the high frequency consonants. Even with this added ear canal resonance, that's no longer enough because of the hearing loss. So hearing aids need to amplify the treble sounds and not the bass, for the most part, for people like this. So when people take ear mold impressions, okay, when they take the impression of the ear to make the shape of the ear mold. Now, I'm going to stop sharing for a second here and take out my little bag of hearing aids. All marked. Okay, here we go. This is a behind the ear hearing aid. This is the hearing aid. This is the tubing, and this is the ear mold. And this is sort of a high power hearing aid that's meant to fit inside the guy's ear. Okay, so I would be putting this inside of my ear like so, and then the hearing aid would be wrapped behind my ear. So essentially looking like that, okay? Now, most hearing aids don't look like this anymore. Most hearing aids today look like this. Very small, and they have a thin tube, and then they got this thing here. Now, this hearing aid, I'll put it in my ear. Take this one out and put this one in. Okay? Let's talk turkey here. All right. And that little tube thing, and stick that in the concha here. Having a little difficulty here, but I'll get it. Okay, so when this is in my ear, you'd hardly notice I had anything there. Okay, so this is more like today's hearing aids. This is kind of more like yesterday's hearing aids, but you still see these for high power hearing aids, for people who have a big hearing loss. Now let's look at the pieces and parts of a hearing aid. Okay, you open up the battery door, close it. You got an on-off switch. You have a volume control on the hearing aid, and you open this up, and you'll see a tiny little microphone. Let's see if I can show you that. There, see that little dot? That's a microphone. That's what's picking up the sound. The hearing aid makes it louder, and then pushes the sound through this ear hook, through this tubing. This is a tube, and then this is the ear mold. Okay? Today's hearing aids are quite similar. If I take this one out, it'll have a microphone underneath here, and the sound goes through the tube and into this little round thing that sticks in the ear. This is called a dome. Okay? And you can pick the size of dome you want for the size of ear canal. And this is not a high power hearing aid. You still see these for people who have real hearing loss. So if you see this kind of hearing aid on somebody, you know they have quite a big hearing loss. Okay? If you see this hearing aid on somebody, you think, oh, we've got an average hearing loss. Probably about 50 or 60 decibels. This guy's got like an 80 or 90 decibel hearing loss, big hearing loss, okay? Anyway, this is very thin tube, but it works on the same principle. Only it doesn't have to have a custom-made ear mold like this, okay? You just choose a stock dome. And then this weird little thing that sticks out, that's just meant to fit in the concha bowl itself to help anchor this little dome in the ear. Okay, that's all that is. So pieces and parts of hearing aids. Okay, here I'll show you an ugly old all in the ear hearing aid. Okay, and its microphone will be on the outside as well somewhere. Let's see if I can show you where the microphone would be. The microphone would be just a little kind of, let's see, well, it's a tiny little dot. See if I can show it to you just for fun here. Oh, here. It's going to be this tiny little white thing right there. Okay, tiny little white thing. Anyway, its battery door opens up. And it's volume control here that you can turn. And then the sound comes out of that white thing. But what's that little hole there? And When you're looking at this, see the tubing goes into the mold to put the sound, but there's another hole. What's with that second hole? How come at the end there's two holes? Well, that second hole is called a vent. And look at this guy here. Look, it's got holes in the dome. Those holes are called vents. Okay? Vents are very important pieces of hearing aids. Vents are a non-electronic acoustic modification. And you know why you have vents? To reduce the occlusion effect. Put your finger in your ear and talk. And when you put your finger in your ear and talk, you hear yourself louder in the ear that's plugged. Well, that's exactly what a hearing aid's going to do. It's going to plug up your ear and you're going to hear your voice too loud. That's why you have a vent, to reduce the occlusion effect. And almost all hearing aids use them, except really high power hearing aids. Let's share screen now and go to our notes and kind of continue from where we left off here. All right. That's what it said here. For high power BTEs, beware of old narrow tubing. And that would be happening when the tubing in the hearing aid got to be really old and cracked and got really narrow. And when you make things really narrow or thin, you cut off the highs. And let me show you what I mean there. I'll just grab a piece of paper here. Let's see, I'll grab this piece of paper here. Here's the paper. And I'll roll it up like a horn. Okay? Now, if I'm talking into the wide end of the horn, my voice is going to get muffled. Okay? So when you make something narrow, you cut off the highs. Whereas if I talk to you from the narrow end and it gets wider, you hear the high frequency so much better. Okay? That's simple. That's another non-electronic acoustic modification. Didn't use any electricity to do that. Okay? That's the second one. It's called a horn. And so when tubing in behind the ear hearing aids, BTE, behind the ear hearing aids, gets to be really narrow, it cuts off the high. So that's when you, the HIS, would replace the tubing. You'll yank it out and you'll take some glue and you'll put new tubing in. And I'll show you what that new tubing can look like. So here you go. It's all part and pieces. So when you're talking ear molds, the types and materials, ear molds for high power behind the ear hearing aids, okay? So I'll show you a picture here of ear molds. This is a picture of various types of ear molds used in high power behind the ear hearing aids. There is a solid one. The main two I want you to look at in this picture are here and the middle one. This one fills the whole concha bowl. There's almost no vent in it because the person has such a bad hearing loss that even the occlusion effect, you want that because you want everything you can get, okay? It's made out of a soft material like silicone. You can squish it. Squish, 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 okay? This ear mold here is made out of plexiglass. It's called Lucite, L-U-C-I-T-E, Lucite. And they have tubing going in, and it will likely have a vent. So this is for really high power behind the ear hearing aids. And when you see someone walking around with a whitish looking filled ear concha bowl with a great big behind the ear hearing aid sitting behind it, you know the guy's almost deaf, okay, has a huge hearing loss. If you see someone like this, you'd say the person has a fairly severe hearing loss. This one's called a Lucite skeleton. A Lucite skeleton ear mold. This one's called a full shell silicone ear mold. This one's silicone, this one's made out of Lucite, like plexiglass. Now, silicone prevents feedback. If you're filling up the whole ear, and I'll stop sharing for just a second here, if you fill up the entire ear with a full concha ear mold impression, and let's see if I can show you one of those, because I have one of those too. There you go. Look at that puppy. Okay, big behind the ear hearing aid, great big honker. Off and on switch. The battery door again. To open up the here, I'll turn it this way. The battery door. Close the battery door. Volume control on the hearing aid. Right there. And the microphone on the top of the hearing aid. If I turn this and face you, you can see that little hole. And then this is called the ear hook. Ear hook. This is the tubing going into a silicone. See how I can squeeze it? Full shell ear mold. Full concha bowl. So this is for someone with a whopper of a hearing loss. Notice there's no vent in there. Here is a lucite skeleton ear mold. Okay? And the lucite skeleton ear mold, see how it has two holes? Two pathways. Here's the tube. And the sound goes through the top tunnel. But here is the bottom one. And look at this. I can stick my screwdriver right through it almost. Okay? There you go. That's a vent to stop the occlusion effect. And here's a series of vents in the dome of a lesser power hearing aid. And this is the very common style you'll see today. Very common. All right, back to share screen. All right, so mainly the two types of ear molds, full shell, silicone, lucite, skeleton. And the tubing is called number 13. Don't ask me why. It's called number 13 tubing. And number 13 tubing is, and I'm going to stop sharing so you can see this again. Number 13 tubing is, if I pull it off, 2 millimeters in diameter. You see that? 2 millimeters in diameter. That's the width, or that's how open it is. That's the diameter. Okay? When you have this kind of hearing aid, okay, this is called thin tube, because if I hold this one up, look at how thin it is comparison. And this one is less than 1 millimeter diameter, about 0.8 to 0.9 millimeters diameter. This one's 2 millimeters diameter. Okay, you can see the vents clearly. Bottom here, and in the dome, you can see it right there, the holes. All right, very good. We're getting someplace here. Let's carry on more with our notes, however, so that we can move along in an organized fashion. Okay, so there you go. Ear mold types. General frequencies of ear mold acoustics: venting, filtering, horns. 3 acoustic modifications. 1, 2, 3. And the most important one we use today is venting. But we'll mention all the other ones. Venting reduces the occlusion effect. It controls low frequencies. Damping or filtering affects the mids. And horns affects the highs. So when you're looking at it in an organized fashion like this, venting affects the lows, damping affects the mids, horns affects the highs. Back to our notes. Horns and filters were relied upon heavily in yesterday's hearing aids. They aren't used much today because today's hearing aids are digital and they're very, very flexible, and you can get anything you want at Alice's Restaurant, so we don't rely on them as much today. There is always a tension between vents, horns, and feedback. Horns increase the highs, but highs might leak out of the vent. Now, let's talk turkey here. What's feedback? That's the whistle that you get with hearing aids. You might have heard it yourself on people who have hearing aids. They're taking the hearing aid out and it's whistling, okay? So what is feedback? Highs bounce, lows bend, right? Low frequencies are long waves and they bend around things, but highs are really short and they bounce off of things. What happens if you have a high power hearing aid and it's putting sound in the ear canal and the sound is bouncing off the drum and it leaks out of the vent that you had to reduce the occlusion effect, and it gets picked up by the mic. And it gets amplified, and the sound hits the eardrum and bounces off and gets picked up by the mic. And you got a loop. It's just like you talking in a mic, and you go too close to the speaker, and you get feedback. That meow, and that's because now sound from the speaker itself is entering the mic. Not just your voice, but sound from the speaker. And you're getting this vicious loop. Okay, and you want to stop that. That's why I say there's a bit of a tension between the size of the vent that you might want to use to reduce the occlusion effect and, you know, and horns, let's say, that would try to amplify the highs. Or even if you're not using horns anymore today, which we don't much anymore, okay, and I'll show you what those look like too, okay. By the way, I think I could even. I'll show you what a horn was. A horn, and this is just showing you an earplug, okay? But it's showing number 13 tubing, and this tubing gets wider as it rounds the corner. See how it gets wider? So it's no longer 2 millimeters in diameter, now it's 3. So that diameter is bigger than this diameter. This is 2 millimeters in diameter, this is 3. That's a horn. Okay, horns were used to amplify the highs, and it helped because analog hearing aids didn't have the flexibility we do today. Oops. All right, we didn't have the flexibility to do that yesterday, so we relied on horns more. Now, they didn't have yellow things like this. It was on an ear mold, okay? The horn would actually be in the ear mold itself, but it would get, the tubing would get wider around the corner, and then the hole in the end of the ear mold would be to accommodate that 3 millimeter diameter tubing. So the number 13 tubing, which is 2 millimeters in diameter, when it rounds the corner, it would get a little wider. And that's the horn effect, okay? Increases the highs. But there you can see there's a tension there. Because if you got a lot of high frequencies, those are the ones that are going to bounce out and leak out and get picked up by the mic. Again, causing feedback. That's what I mean by that tension. We don't have to worry that much about that today anymore because today's hearing aids have automatic feedback reduction. Believe it or not, automatic feedback reduction. The hearing aid will detect the frequency that's leaking out, and the hearing aid, get this, will actually make an opposite phase high frequency tone to cancel out the feedback. Yeah, so today's hearing aids have come a long way from the beige bananas that sat behind someone's ear of yesterday. So let's look more at venting in particular, because venting is the most important one. It's a short hole in the ear mold done to reduce low frequency amplification. It creates more acoustic mass and lets the lows therefore leak out. The bigger the vent, the more the lows escape. Venting reduces the occlusion effect. Now let's write down in our margin. Let's really make sure we know what the occlusion effect is. There's two definitions for the occlusion effect. First, there's the lay common definition. Your voice gets louder when your ear's plugged. Okay, your voice gets louder in the ear that's plugged. That's the easy definition. Now the professional definition that we as HISs need to know. It's got 5 steps. Low frequency, bone conducted sounds, because your voice is not only coming by air, but it's also traveling by bone, right? That's why you hear yourself differently than others hear you. When you listen to a recording of yourself, you are hearing yourself only by air conduction. You're not hearing yourself by the way you hear when you hear a recording, you're only hearing yourself through the air. And that's how other people hear you. But you hear yourself through the air and through bone. Anyway, and what resonates with lows? Mass. So low frequency, bone conducted sounds, number 2, resonate the mass of the skull. Number 3. Low frequency, bone conducted sounds resonate the mass of your skull, which in turn, number 4, resonates the cartilaginous portion of your ear canal. And number 5, plugging your ear prevents that added resonance from escaping. Okay, so 5 little Indians, 5 little steps. Low frequency bone conducted sounds resonate the mass of the skull, which in turn resonates the cartilaginous portion. Plugging your ear prevents that from escaping. And the more the cartilaginous portion is involved, the more occlusion effect you have. So if you put your finger in your ear, you've got a bit of an occlusion effect. Do that. And now put your palm against your ear. You get way more. Okay? Here you get occlusion effect. Here you get way more occlusion effect. Experiment, do that for yourself, okay? When you put your palm against your ear, your whole cartilaginous portion is involved. Whereas when you put your finger in your ear, less of the cartilaginous portion is involved, okay? Occlusion effect is a big one. What's the biggest complaint of hearing aids? Background noise. What's the second major complaint of hearing aids? Occlusion effect. Okay, so occlusion effect is a big one. And that's one we need to know when we talk about vents. Venting reduces the occlusion effect, and you know why and how it does? Because you are increasing the acoustic mass of air. What do I mean by that? I'm letting the air trapped behind the eardrum communicate with air outside because I've got a hole in the mold. So now I've increased the acoustic mass of air. And lows are going to follow that acoustic mass like Hansel and Gretel followed the breadcrumbs to get out of the woods. Okay? Lows like mass. So vents increase the acoustic mass of air in your ear canal. And the lows therefore escape. They follow that. So your loud, the low frequencies caused by your voice can escape out. And that reduces the occlusion effect. The bigger the vent, the more drop in low frequencies in your ear canal. So now we'll look at our notes here to make it make sense. Venting reduces the occlusion effect. So that's what this top stuff right here is all about. And in some hearing aids, you had what they call a select vent. You could choose the size of the vent you wanted to use. So here's again, venting, filters, which we almost never use today, and here's a horn, the number 13 tubing getting bigger. Select vent. Here's the number 13 tubing, and here's the vent, a hole that was burred in the ear mold, and you could choose the size you wanted. You could choose a smaller one, bigger one, bigger one, bigger one, bigger one. Okay, you could choose the size, just depending on what the guy said. How did his voice sound? Try this one. How did this one sound? So these were like a series of plugs. Now, if I show you to you what that can look like, I'll stop sharing. Here's some select vents. Okay, when you look closely at it, can you see the holes getting bigger and bigger? Okay, as you go from left to right. Okay, select vent. You can choose the size of the venting width. All right, very good. Okay, now here's some types of venting procedures. The best one is when the vent is parallel to the sound bore. So this is where the tubing would be put in. The number 13 tubing would be put in here, and here's a parallel vent. Some people made diagonal vents, and those were not as good. They did that, but those tend to let the highs out as well as the lows. So these aren't as good. They did that in order to accommodate small ear canals, but it's a bad practice. Here's a parallel vent that's kind of right at the edge of the ear mold. Again, to accommodate a smaller ear canal, perhaps, that couldn't handle this. So, but here's the effect of venting. A 1 millimeter vent doesn't let much of the lows out at all. A 2 millimeter vent starts letting lows out. 3 millimeter vent, more out. 4 millimeter vent, more lows escape. You see that? The influence of vent diameter on the occlusion effect. That's seen here too. Here it's in terms of dB SPL, output from the hearing aid. Here it's in terms of decibels of gain or amplification of the hearing aid. And remember the difference between dB and dB-SPL. dB is referring to a relative decibel value, like gain, the amount that the hearing aid is amplifying. dB-SPL is an absolute decibel value referenced to 0 dB-SPL. And again, I'll just review that with you to make sure you know the difference. Absolute decibel values refer to the input coming into a hearing aid and the output coming from the hearing aid. Gain is just the lift or the amplification that is given by the hearing aid. And gain is relative. I can give 50 decibels of gain to a 10 dB-SPL input. I can give 50 decibels of gain to a 20 dB-SPL input. I can give 50 to a 30 dB-SPL input. And when you add dB-SPL and dB, you can add them together like 1 plus 2 is 3. Okay? It's only 2 dB-SPL values that you can't add together like that. So a machine making 90 dB-SPL and another machine making 90 dB-SPL, the sum total is 93. But if I have 50 decibels of input, 50 dB-SPL input coming into the mic, and the hearing aid gives 50 dB of gain to that sound, my output is 100. 50 plus 50 is 100. You can add an absolute and a relative together like 1 plus 2 is 3. So that's the beauty of our field, is we can do that. Anyway, the effect of vents is seen in dB-SPL or in terms of simple dB. And again, the wider you make the vent, the more the lows escape. Venting ranges in size from 1 to 4 millimeters. 1 to 4 millimeters. A 1 millimeter vent is simply called, and if I stop, hang on, I don't want to, I just want to escape out of here and look at the notes and stick to this. A pressure vent is a 1 millimeter vent. A pressure vent hardly lets out any lows at all. A pressure vent is just there for simple comfort, so that you got a little bit of air communicating outside versus inside the ear canal. It just keeps the ear canal less damp. It's mostly meant so that when you take the hearing aid out of the ear, you don't yank out the eardrum and the ossicles along with it. Okay, pressure vent is a comfort issue only, not really meant to modify acoustics or decrease the occlusion effect. Note on PowerPoint slides where vents are seen on BTEs behind the ear hearing aids and ITEs. Stop sharing and start looking. So, the white is where the sound comes out. The other hole is the vent. And if we turn the hearing aid around, there is the other side. There's the vent. Okay, that hole continues with the bottom hole. And you can tell this is a right ear hearing aid because the writing on here, the serial number and stuff, is in red. Red is always the right ear, blue is always the left ear. This is called an ITE, in the ear, ugly. Hardly anybody wears these. This is a smaller in the ear hearing aid. And you can even see a little piece of fishing line that someone would have to grab to pull the hearing aid out. Once again, if I turn it to face you, there's the hole for the sound, there's the hole for the vent. That hole continues with, here, there. Okay? And again, a battery door on the hearing aid. This would be the mic, okay? The battery door, the vent, piece of fishing line so the guy can actually pull it out of his ear. This is called an ITC, in the canal. In the canal. A little bit smaller than the ITE, full shell ITE. You hardly see this one in the right hand here anymore. You still see these a bit. Let's see if I can show you another hearing aid. Here, this is a left ear hearing aid, a completely in canal hearing aid. CIC, completely in canal. Once again, a vent and the sound, the hole for the sound. Left ear, because it's got blue writing. And again, it's vent, it's battery door, the mic, battery door, vent, piece of fishing line so you can pull the hearing aid out of the ear. So all kinds of neat stuff we have here, you know. Now let's go to, okay, let's go to our notes here so we can carry on. And let's move on down here. There you go. Our second acoustic modification is called a filter. You barely see these anymore. They were tiny screens that caused turbulence, and their purpose was to smooth the frequency response of the hearing aid and to reduce the peaks, because it was the peaks in the hearing aids that caused feedback. So if I show you a PowerPoint slide of that, here's a frequency response of a hearing aid. And you can see a peak and another peak and another one and another one and another one. These are natural resonances from the internal plumbing, we'll call it, of the hearing aid itself. Okay? Natural resonances taking place inside the hearing aid. And if left unattended, they can cause feedback, because you see how they're in the high frequencies, mid to highs. And these peaks are what cause feedback. So filters were meant to dampen the peaks, to smooth the frequency response. And they were tiny screens stuck in the hearing aid. Now, where were they in the hearing aid? I'll show you. Okay, I'll stop sharing and I'll show you where they are. In this hearing aid here, the filter is that tiny red thing right where I'm going to show it to you if I can point. Here's my screwdriver here. The tiny, I hold it this way with my right hand, it's probably easier. This tiny red thing right here. Okay, see that little red dot? That's a filter. It's a little screen. So in this hearing aid, the sound was coming into the mic, that little hole. The hearing aid amplifies the sound and spits it out. And right where my finger is here, this is called, inside the hearing aid, you can't see it, but inside the hearing aid, the speaker. And the speaker, they call it in hearing aid lingo, they call that the receiver. Why the receiver if it's spitting out sound? Well, engineers say it's what receives the electronic current. It receives everything. And the receiver simply changes electricity back into sound. What is a mic? It changes sound into electricity. A mic is a transducer. Transducing means changing energy from one form to another form. Microphones and speakers are backward from each other. A mic changes sound into electricity. A speaker changes electricity into sound. A speaker is a backward mic. A mic is a backward speaker. A smile is an upside-down frown. A frown is an upside-down smile. Good. Transducers. Hearing aids are two transducers, a mic and a receiver. And think of the receiver as the speaker. Okay? So filters are right beyond the speaker, and they smooth the frequency response. And they do that by providing a tiny little screen, and that's stuck in the ear hook. Okay? I'll show you another example of a filter. This is another behind the ear hearing aid, and I've taken off the mold. Okay, the mold is taken off from this hearing aid. And in this particular hearing aid, the filter is at the end. Let's see if I can show you here. It's kind of hard to see, but it's right at the end. So in the first hearing aid I showed you, the filter was kind of right, you know, here. And in this hearing aid here, the filter is right at the very end. Kind of hard to see, I know. Okay, I can see it more easily than you, but again, it's a tiny little screen stuck in the ear hook. Okay. The more finely meshed it was, the more turbulence it created, the more it dampened the peaks. So, and they called filters that they were measured in ohms. This one had fewer ohms, this one had more ohms. Ohms are a measure of resistance. Filters were resistors. They dampened the peaks wherever the peaks were. You remember the word impedance? It was comprised of reactance plus resistance. Resistance to sound is simple friction. Reactance is opposition due to stiffness and opposition due to mass. Right? Mass resonates with lows, mass opposes highs. Stiffness resonates with highs, stiffness opposes lows. So those oppositions were called reactance, to sound, resistance in any object to the passage of sound is equal for all frequencies, and that's what filters are. They are resistors, and they dampen the peaks wherever the peaks may be. And in most hearing aids, the biggest peaks are in the mid to highs, so that's where the effect of filters was. They were used to reduce the peaks and thereby reduce feedback, and also they improve the quality of sound. So if I escape out of here and go to our notes, you'll see all of that written here. Feedback, resistance, da-da-da. The largest peak in old behind-the-ear hearing aids was at 1,000 hertz. So that's where filters did most of their action. Location of filters at the small end of a behind-the-ear ear hook. In the ear hearing aids, it was right next to the speaker. And you can kind of see it. If I show you here, in an in-the-ear hearing aid, or maybe if I'm going to share screen, I might have a picture of it. This is where we're really going back and forth here, aren't we? That's okay. See if I got pictures of any of these things. Oh yeah, here's a picture of the location of filters. Look at that. Okay, often at the end of the ear hook, and again over there. Okay, in BTEs. In ITEs, it would more likely be in at the very end here. See that little white thing? It would be just behind that little white thing. So the speaker in an ITE hearing aid, the mic is of course going to be on the outside over here, and then the speaker is going to be behind that little white thing. That little white thing is actually a wax guard. You can replace those. Clients can replace those. They're given a little tiny tool to stick it in there and pull out the wax guard and put a new one in. Because if the speaker's plugged with wax, no sound's going to come out. And behind the wax guard would be the filter. Okay? So between the speaker and the wax guard would be the filter. You'll learn more about that in your labs and stuff too. This is just kind of an introduction to hearing aids and their non-electronic acoustic modifications. So let's look at the basic parts of a large behind-the-ear hearing aid. The mic, the hearing aid, the ear hook, the filter usually would be there, the number 13 tubing, the lucite skeleton ear mold. Here's where the sound goes, and here's the vent. Large behind-the-ear hearing aid, number 13 tubing. Once again, the mic, volume control, off-on switch, battery compartment, mic, ear, inside here would be the speaker or receiver, ear hook that you can twist, you can turn it off, you can twist it off and screw it back on. You stick the number 13 tubing on the end of the ear hook, there it is, and here's the vent. And this would be a lucite skeleton ear mold because you can see that hole in it there. The vent and the skeleton portion. Whoops. Okay, so, and here's the last acoustic modifier. So here's what filters we're doing. Dampening the peaks. The more ohms, the more they dampen the peaks. Now, and then here's a picture showing you the location of filters. Nobody worries about that, so leave that one alone. So now, here is a horn. And a horn, as we said, is a widening of the actual tubing. And when you increase the exit diameter, you've increased the highs. But if you did the opposite, you decrease the highs. So horns were meant to, they were at, and remember I said they are at around the corner of the tubing. Pretend this has a regular mold on it. Around the corner of the tubing, the diameter gets wider. Okay, that's a horn. And the effect of a horn is, of course, going to be to increase the high frequencies. As you can see here, the bigger the horn diameter, the more the highs were increased by a few decibels, like 5 to 10 dB. Here's a reverse horn. Make it really skinny. You're going to really cut off the highs. Leave it alone in the middle, okay. Or if you make it bigger and bigger, you increase the highs. So again, here we're just about at the end of our Zoom session. You have 3 electronic, non-electronic modifications. Vents, filters hardly used anymore, horns hardly used anymore. The biggest one you need to know is venting. Here's a picture of number 13 tubing. You will be learning how to replace number 13 tubing. But not many people are using number 13 tubing anymore, except people with the high power hearing aids that have a real severe loss. Most hearing aids today fall into this camp. This is called a thin tube BTE, behind the ear. I'll move this out of the way so you can see, smaller with a tiny sound tube. So you would think that would really block off the highs, but the hearing aid pumps out a whole bunch more highs to counteract the fact that this is narrower. The occlusion effect gets reduced because this dome here has a lot of holes in it. And it's got the cosmetics of a completely in-canal hearing aid without the problems of a completely in-canal hearing aid. Because completely in-canal hearing aids get clogged up with wax easily. They're way deeper in the canal. So completely in-canal hearing aids were high-maintenance hearing aids. These hearing aids that were very, very, very tiny, okay? So let's see if I got another picture here. Now, here's another thin tube open fit BTE. So here's the picture of it. There's the one I showed you. And here's how it would sit in the ear. There's the dome with its vent, its holes in it. And there's that little extra piece that I was showing you that helps to anchor the dome, to help this situated nicely in the ear canal. This little piece of plastic is just sort of a little string that to go in the concha to anchor things. And you can see it on the left over here. Okay? Now that's the open fit BTE, but the thin tubes, you know, would cut off the highs. Here's a regular 2 millimeter number 13 tubing, okay? And here is the thin tube. Okay, the 2cc just means the coupler that they were measuring things. Don't worry about that. Just know thin tubes would cut it off. And thin tubes are less than 1 millimeter in diameter. So the hearing aids have to counteract that by deliberately producing more treble amplification. Here's the most popular. This is a receiver in canal hearing aid, and it looks identical to the thin tube hearing aid. So I'm going to stop sharing and show you. On the picture, they're identical too. So, and I'll show you as well as we'll finish here, okay? Here's a thin tube. The receiver or speaker is here, and sound goes through the tube and into the guy's ear. When you've got receiver in canal, the receiver is in the canal, and the dome is put over the here. So sound doesn't go through the tube. There's a wire. So the battery is here, and the hearing aid amplifies, but the receiver, instead of being at the top here and having a tube that the sound goes through, they put the receiver in the ear, and they're connecting the receiver to the hearing aid with a wire. Here it says it looks a lot like thin tube, except here a wire goes through the tube, linking the amp to the receiver, which is inside the dome. Like thin tube BTEs, the occlusion effect is reduced, and the cosmetics of a CIC without the problems of a CIC. Here's a picture of one close up. Here's the hearing aid, and the wire goes through the tube. And the receiver is inside here. I'll show you now here. In my left hand, thin tube BTE. In my right hand, completely in canal. They look almost identical. It's just that inside of this one, there's a wire. It's hard for you to see that, so it's hard to believe that, okay? But they look almost identical. But inside of here, if I take off the dome, there's the receiver. Okay, the receiver, the tiny little speaker. All right, I'll put that guy back on because I don't want to lose it. All right. So the most receiver in canal hearing aids are a little bit more expensive than thin tube. They're a little bit better. This is one style of it. You can have another style of it. I mean, a different by a different company. There's a different company, okay? You got many different companies making thin tube BTEs as well. They don't always have to look exactly like that, but the point is they are smaller than the beige big honkers like this. I mean, look at the size of this compared to this. They're both BTEs. They're both behind the ear hearing aids. But you hardly see these anymore, okay? Only for high power hearing aids. This is by far the most common. Stop sharing or start sharing, and look where we have today. Okay, it's the end of our slideshow. So we've gone through everything. Okay, if I get out of here and look at what you can see in your notes, horns we talk about, not used much today, location of horns at the end of BTE ear mold tubing, in ITEs at the end of the casing surrounding the receiver, but don't worry about it, you don't see them much anymore at all. Horns were basically 3 millimeter, and they called them Libby horns, 3 millimeter Libby horn. You hardly see them anymore. Tubing in BTEs, for regular BTEs where lots of gain is required, the most common is number 13. 2 millimeters, more width gives more highs like a horn. Okay. Clients with high power BTEs, again, beware of old narrow tubing, so you'll have to change that. Open fit thin tubing is narrower in diameter. Note what that would do to the frequency response. The hearing aid therefore has to make up for that high frequency loss, and never confuse thin tube open fit BTEs with receiver in canal BTEs. They look the same, but they are different, and holding them up again to highlight that difference. Okay? A RIC hearing aid, receiver in canal versus a thin tube hearing aid. Okay, both of them use domes. Both of them, look at the venting. Okay, you can change the domes. You can have domes that have less venting, that allow more venting. Okay, larger domes for bigger ear canals, smaller domes for smaller ear canals. The hearing aid companies give that stuff to you. Anyway, I'm glad to see that my little microphone is still bobbing up and down here. We are basically done this unit. We are done this course. Maybe we can have a review in early May. I'm gone to the Netherlands, Holland, in Europe from April 20 to April 30. And there's those few days in early May, in that first week of May, before your final exams. We may or may not hold a Zoom session there. Let's stay in touch. I'll talk to you about it more as we get to that time, but consider us essentially done our acoustics course. All right, I'll stop recording now.